Now let's again look quickly at some important statistics of the random variables that we have known already earlier. Now the first one is the expected value or the mean. You know already that is the weighted average of all possible outcomes. Remember, possible outcomes even when you don't see it. Now in a continuous case, it's the weight being the density. Before with the discrete case, the weight were the probability, right? And now it's the density. So we adapt it to the notation and to the formality of continuous random variables. Instead of sum, we take the integrals across the whole possible range of the variables with y times fy when y change along that range. Okay, and this expected outcome, especially for the continuous case, usually denoted as the Greek letter mu. R as before, E with Y, the capital Y in the curly bracket, right? And that's one statistic, so it's the weighted average of all possible outcomes. Keep that mantra in mind. The median. The median is another way to look at the middle point or somewhere between the average of the distribution. So the median is the point in which you have exactly 50% of the observation below that point and 50% of the observation or the outcome above that value, right? So the medians here denoted as M. Now, so you must have the probability that Y falls below M is not smaller than 0.5, but also not larger than 0.5, exactly 50%. Now, keep in mind, those two, usually when you read on the media or in the daily context, you see on the TV when they talk about the average, usually they use one of these two. However, in no way that is the most likely outcome. So I don't know about you, but from my experience, my mind somehow directly tied that to the most possible outcome directly, automatically. And that is like a bias, a cognitive bias. When we talk about the most likely, the most probable outcomes, we talk about the mode. So it is the value of y for which the density function of y takes it maximum. So in a discrete case, the probability, not the density, then, but the probability takes maximum. So that's the most probable outcomes. However, again, keep in mind, doesn't matter how probable it is, as long as that's random variables. Other extreme events, they have a chance to occur as well, even though when the chance is small. Now, that's just something we should keep in mind. Now go back here. There's one thing I forgot to mention actually, is how about the expectation of a function g of the random variable y. Oh, sorry, this should be the normal bracket now, and then the square bracket. So formally, it would equal the integrals from minus infinity to plus infinity of g y times f y times dy. Now, this you will see here and there as we go. Okay, now let's look at one example of continuous random variables. And the example in this case is the uniform distribution that we look at now. So a uniform distribution usually denoted as U of A and B, Y, A and B. A and B is the range of value between those the random variables is distributed. Now, so when we talk about a continuous random variables, we first talk about the probability density function, denoted as small f of y equals, so what wrote on your slide is 1 over b minus a with y falls within the range of a and b, right? However, to make it clearer, let's write something else, or the probability density function will receive the value of 0 otherwise. Otherwise means when y is not within this range. No? And then we would also have the cumulative density function, y equals y minus a over b minus a. So usually you would have to take the integral of the PDF, right? But in this case, because it's a uniform distribution, somehow easy to calculate. So the formula is given here, we will see. So now if you put it on the graph, it will look like this. Now, y, and here is f y. Assume A is here and B is here, and this is 1 over B minus A. Relatively only now, not exactly the scale of the ratio. Okay, so outside of the range A to B, the density function, the PDF, receive value of 0. Let's put 0 here, and here is 0 now. But within the range between A and B, what is the value of the PDF? Let's mark it here. Okay, so it's like this, and it's constant. Oops, not very straight, but it's supposed to be the straight line. You have to use your imagination a bit when I draw something. Then it's not straight again. Anyhow, okay. So this line is the PDF of a uniform distribution, and it's constant over the range between A and B. Now the first task asks we to calculate something analytically. First is the expected value of y. So the expected value, let's put it formal, is the integral from minus infinity to plus infinity, right, of the outcomes, the possible outcomes, times the PDF, probability density function itself, when we evaluate it from minus infinity to plus infinity. However, because outside the range from A to B, fy 0, so we could just simply write it from A to B, right? We only care about this range, times y, and then you plug the f y in, which is here, 1 over b minus a times dy, right? I know it's scary that we're doing integrals right now, but at least try one to see what it is. Now, and because 1 over b minus a is constant, a and b are two constants, right? We could put it outside of the integrals. So 1 over b minus a times the integrals of from a until b of y times dy. Now, here we have to use a bit of the integral law, the law of taking, or the rule of taking integrals. However, here in this case, trivial. You can just simply think about which function that when you take the derivative will yield y. 1 over b minus a, we write, put a bracket for clearer. That's actually 1 over 2 times y squared, evaluated from a to b. So actually, if you take the derivative of this part, what will you get? You get the y itself. So that's the idea of the integrals. Finding a function that when you take the derivative will equal to the function inside the integral. Now rewrite it further. Again, 1 over b minus a, rewrite. 1 over 2 rewrite because it's constant. What does that mean with this bar and then AB? Meaning you plug a and b to the function y squared, b squared minus a squared. So that is that. Now we can plug in the value. Equals A0, right? It's written on the slide. Yep. And B, plug in, equals 1. We would have the expected value of y now equals 1 over 1 minus 0 times 1 half of 1 square minus 0 square. Because 1 over 1 minus 0 is 1 times 0.5, and inside this bracket again is 1. At the end we have 0.5, right? So that is the expected value of the uniform random variable y. And you can notice because the interval between a and b is 1, this is actually exactly half of the way, right? So here is e y equal 0.5 in our example. Now, how to calculate the probability that P of, now I have to make some border so that I don't mess up the other. Then let's move P a bit upper so we have enough space. P, the probability that 0 now, y falls between 0 and 0.5. There's two ways. first we take the integral of the f, the small f, right? So it could either is 0 until 0.5 f y dy. So you plug this in here and calculate the integrals. In this case, actually easy because the fy is the constant. So now, not much to do. However, easier ways, we just simply use this formula, right? Because the random variable y is distributed from 0 until 1. So we can just use this, meaning it's equivalent to the probability that y smaller than 0.5 equals f 0.5, right? We don't have to care about the part to the left of 0 because only start from 0. And then we plug in the formulas over here. Y is now 0.5, right? Minus h is 0 over b is 1 minus h is 0. Sorry, I should write it 0 here. And here 0. At the end we have 0.5 over 1, which is 0.5. So the probability that y is smaller or equal to 0.5 is exactly 0.5. So it's half of the area here. Now, so the area here is, if you take the height, in this case the fy, times the width of this rectangle, which is 0.5, you will also get the same result here. So that says when the distribution is uniform, it's a special case, because before the idea of the integrals is calculating the area below the curve. So here we're doing exactly the same, but because here the height of the PDF is the same everywhere within A and B, we don't have to do the integral. We can just calculate it directly. So that may suggest you the idea why integrals is used. It's just a special method to calculate the area under the curve when the curve is not something trivial like the rectangle. Now let's draw sample from a uniform distribution in R. Here again, let's fix the number of observation or the sample size as 1000 now, and draw a sample of 1000 observations from the uniform distribution. Now note here, however, you see that the uniform distribution has a certain range of value within that it distributed from A to B. So here by default in R, when you don't specify A and B, it ultimately assign A 0 and B is 1, like the example we are having. So let's see. Now you see all those numbers in between 0 and 1. However, if here you specify A, for example, 2, and then B equal to 5, so it's distributed uniformly between 2 and 5, and then you draw it, and you will see now. So let's say the histogram of now distributed between 2 and 5, and unlike the theoretical histogram that we draw here, it's not very evenly distributed, meaning there's some certain range that draw more in the sample, has more observations than the other. No? And then you can also calculate the mean simply by using the mean command, and this is about 3.4. No? So from 2 to 5 should be 3, and divided by 2. No? So the middle point of 2 to 5 should be 3.5 theoretically. No? And here is 3.49, which is quite close already. So now let's go back to the case of 0 and 1. Sorry, 0 and 1 to see what happens. Now the case we have on the slide. So that we draw another sample and plot the histogram here. Again, it's not really evenly distributed, not really uniform distributed, is because it is random sample now. However, when you calculated the mean, also very close to what we have calculated theoretically, which is 0.5. Here we have 0.49. So that's how it works with the uniform distribution and a sample in it. All right, now let's look at the expectation or expected value, a very important concept in distribution and probability theory. Before going directly to what's written on your slide, let's do it step by step. So if we have A and B as two constant, and Y and X are two random variables, then the first thing to remember, the expectation of a constant A times a random variable Y equals A times the expectation of that random variable Y itself. Now, so just move the constant outside. The second thing, now if you have the expectation of the same thing plus or minus another constant B, then that would equal, like before, A times the expectation of Y plus or minus B itself, because the expectation of a constant is a constant itself. Now, the next thing is, if you have the expectation of a sum of two random variables, X and Y and X, then that would equal the sum of the two expectations of two random variables. So EY plus EX. Therefore, we arrive to what's written on your slide, that is the expectation of a sum of constant A times Y plus constant B times X equals A times the expectation of constant Y plus B times the expectation of, one E missing here, E times the expectation of constant variable X, right? So from these operations, one thing we should realize is that expectation or expected value is a linear operator. Linear operator means when you operate it for a constant times the variables or the sum, then it's equivalent of take the expectation of each of the variables in the sum separately are equivalent to the constant times the expectation in this case now. So that's thanks to the linear operator characteristic or property. However, because it's linear operator, now, then if you have the expectation of a function of y, no, it does not automatically equal the function g of the expectation of y itself, right? Why? Let's take a case. For example, if you have the expectation of log x, no, meaning you have like take a random sample of, let's say, a continuous normal distributed random variable x, and then you take the expectation of the log of this value that would be different from you take log of the expectation of x. Now, so first take the expectation of x and then put it into the log function. That will give you a different value compared to first taking log and then taking the weighted average. In the R example that I uploaded on eCampus, there's already one example inside. You can check it yourself. It will give you two different values. Okay. Then, how should it look like? This part. Now, let's make it formal and generic, very generic. The expectation of a function g of a random variable y would be equals to the scalar integrals notation from minus infinity to plus infinity jy times the density probability density function of y with respect to y. Okay? And this is the most general formulation, holds also for nonlinear functions like this log function. Okay. And the last thing I want you to remember is there's a difference between the expected value of the distribution or of the random variable itself and the expected value or the mean of the sample drawn from that distribution. Now, why? Because the expected value of the distribution is a theoretical parameter. That means even though you don't observe every possible outcomes of the distribution, you know that when you take the average, the weighted average of this outcome, you will get that value. You can expect to get that value. That's what's called expected value. No? You don't observe, but you know that. Whereas with the sample case, that's a different story, because everything in that sample that you use to calculate the weighted average is only the things you observe. That's the realized outcome only, not every possible outcome. No? And even though when you draw different samples every time from the same distribution, you will get different mean, sample mean. Why? Because every sample is also random. Every time you get different realization of the random variable. No? Okay. And note very finally that taking expectation or knowing how to operate with the expectation is operated is very important in probability, statistic, econometrics. This is the first central moment to characterize a distribution. However, we also have like higher central moments like the variance, the skewness, the kurtosis you see later, and these higher central moments all based on the concept of expectation, as you will see. And a lot of time papers, especially theoretical papers, base their core ideas started from very basic concepts such as expectation and variance. So don't underappreciate that.